Thank you for the introduction and for this great opportunity for giving me this opportunity to present my work. So today I'm going to talk about Flatland quantum materials and magnetic heterostructures, and this is all the funding sources that was funding some of the research that I'll present about today. So before I begin, so we are primarily a quantum optics group, and the basic fundamental building block of anything that we do starts with a quantum emitter, which is the simplest picture is a two-level system here. And when you have this kind of a system, it is kind of a simple atom, and you try to excite it, you take it in some excited state, and then the atom relaxes, and then it emits a single pulse of photons within a particular interval of time. So that is the hand-wavy definition of quantum emitters, and in general the sources of quantum emitters are atoms, they can be ions, and we study quantum emitters in the solid state, or which are also called as quantum dots or artificial atoms. And the most of the applications of these quantum emitters that we are interested towards is engineering qubits, and mostly photonic qubits. So we study this non-classical light, the anti-bunched light, to prepare this kind of superposition states which you can encode in the polarization degree of freedom of that photon. And some of the other applications are in quantum communications, and this is an example of one of our monolayers with hosting quantum emitters on a waveguide, where you can demonstrate quantum state transfer from the material into your photonics device. And why am I here today? So in my group, we are basically like doing these, using some of these quantum emitters to perform nanoscale sensing, and basically that arises from the fact that whatever qubits we are building are not very good, does not have very good properties which can be used for this kind of computing. So we know any kind of bad qubit for computing will be a very good qubit for sensing based applications, because they strongly interact with these electronic and magnetic field. So that is the entire motivation of my talk today. So what we are trying to do is we are using these spins in 2D magnets, and we are trying to see the potential of these 2D magnetic materials in some of these quantum optical quantum technologies. And the very backbone of this is the existence of magnons in this system, because magnons can be easily coupled to qubit. For example, the magnon, if it has a magnetic moment, then you can use magnetic dipolar coupling to couple these systems to these kind of qubits. The other way of making this interact is by using other quasi-particles like excitons, and that gives you light-based technologies like optospintronics or even optical transduction from a magnetic material to an optical material to get like spin to optical transduction. So that's where we stand, and I'm going to show today that you can basically show some simple coupling of the spins with this exciton to get exciton coupled spin states. We are not there at the magnon state yet. So our device looks like this. So we use a bulk CRPS4, which is a A-type antiferromagnet, and we use a transition metal dichalcogenide, which hosts excitons as well as quantum emitters. So we study the coupling of both excitons, the intrinsic defect excitons in these materials, and also the engineered defects of these transition metal dichalcogenides with this bulk CRPS4. And the reason like why we were using that, because at that time we were trying to measure FGT texture using NV imaging, and like this kind of NV magnetometry, while it works very, very well, these are very good sensors, but it takes a lot of time to actually scan the material. So then what do? You try to prepare CCD with your NV sensors, and you go like that, where your NVs are irradiated on a thick diamond chip or even thin membrane. But at the same time, when you do that, you can see that the positions of the defects can be randomly located within the depth of the material, and the sensitivity of your NV center and the distance of the NV center from your magnetic surface can be different for the same center, which can, it's hard to deconvolute such results. So how do you get over that? So one motivation of using the 2D materials are these materials can conform to any kind of surfaces very easily. So then you can see in the schematic here, you can get a better conformity, and because of the dimensionality, it's a single monolayer thick, you don't have any like uncertainty in the Z position of these emitters. So this is basically the motivation of using the monolayer semiconductors here. And the semiconductors that we generally work with are transition metal dichalcogenide. They have this kind of lattice. So if you look from the side, it is 3 atoms thick. So layer of transition metal sandwiched by 2 layers of chalcogen, and they have a very wide band gap. And the way we probe these TMDCs, like the previous speaker mentioned excitons, so you basically excite this semiconductor, then you have some electrons in the first exciton level, a hole in the valence band. They are very, very strongly bound, and that is one of the exciting things about excitons in 2D materials, that their binding energy is very strong, because the Coulomb interactions are not screened in the bulk in the same way as in the 2D material. So that's basically the motivation of using 2D materials here. And from the point of view of transduction, if you can really couple these magnetic materials with these broadband 2D materials that are available in the TMDs, you can basically cover most of the optical range than using a single material. So this was at room temperature. Now at low temperature, when we take the same spectra, you can resolve the neutral exciton and the charged exciton. So again, like the speaker before me already explained what charged excitons are. So you have a single electron hole pair, and then this is electron or a hole attached to the exciton. And in addition to these delocalized excitons that are present in the system, we also observe these very narrow spatially and spectrally localized quantum emitters in these materials. And the origin of these quantum emitters are a combination of the presence of defects and strain in the material, which helps the exciton to funnel right at the position of the defect, and in that way you can spatially isolate a single exciton in this material and improve the spatial resolution of whatever it is that you are measuring with these localized excitons. So this is the one feature that we leverage on to study these magnetic heterostructures. The other feature that we use are the exciton degrees of freedom. So this is again the crystal structure, and in the reciprocal space you also have this hexagonal reciprocal space. So that gives you the 6 points in the Brillouin zone, and these are energy degenerate with the K prime and K plus. So what this gives you are optical selection rules that you can leverage to pump a particular kind of spin in one valley using a sigma plus polarized light, and with the sigma plus minus polarized light you can basically populate the other spin in the other valley. And the spins are of course locked to the valleys, and this is what the picture is at 0 magnetic field. So let's say, like, because they are energy degenerate, they have the same colors. If you see the sigma plus and sigma minus light, there will be no change in the energies. So now when you apply a magnetic field, you break this excitonic degeneracy, and what happens as a result of that, you have a valley Zeeman splitting between the K and the minus K valleys, and in addition to that you also have a decrease in a change in the polarization contrast of the sigma minus versus sigma plus. So these are the 2 parameters that you can use to track the magnetic properties of any materials that you are using in the heterostructure, and these are the 2 main degrees of freedom that we will be using. One is the difference in energetic splitting as a function of the coupling with the magnetic material, and also the change in the rho polarization contrast. So the change in color represents basically the change in the energy as well as the polarization, and these are the 2 things that we will be tracking. So we did this measurements just to study valley Zeeman effect by applying an external magnetic field, and here you can see just for the delocalized excitons as well as the trions, you can get a valley Zeeman splitting, and that splitting is of the order of few MeVs as you apply an external magnetic field. So this valley Zeeman effect is also observed for the localized and quantized excitons, and because their G factor is much higher, you can actually get a very large splitting of about 3 MeVs for these localized excitons. So both the delocalized and localized excitons can in principle be used to track some of the properties in these magnetic heterostructures. So again, like, this is our schematic. So we use a monolayer of tungsten diselenide which hosts the different kind of excitons that I am going to show you. And then we have the bulk CrPs4. So this is also a A-type antiferromagnet, but at the same time it is a semiconducting material which is optically active. So it has its own emission properties, and it has this A-type antiferromagnetic order. So and another interesting feature is the Magnon frequency of this material is in the terahertz range, which offers an added advantage of speed. So of course, we are not alone here. There have been several reports that has been shown previously with our most favorite material, which are the CR-SBR, and people are, there is a very nice article, actually a perspective article on CR-SBR and other A-type antiferromagnets that studies that why is CR-SBR alone, like the magnon-based exciton coupling is only seen in this material, and they were basically comparing the differences of CR-SBR with other A-type AFMs like chrome triiodide and NiPs3, and one of the differences is in the excitonic properties of this CR-SBR, which has these very high delocalization of the excitons, and also the transport, the mobility in the CR-SBR is higher than the other A-type antiferromagnets. So there is still some motivation to study excitons which provide this kind of delocalization like CR-SBR with the added advantage of mobility, which the other optically active antiferromagnets do not really offer. So then the idea is to like see and observe these kind of magnetic heterostructures by taking the best of both worlds, where you can get like high magnon frequencies in these antiferromagnets, compare added with the added benefit of tightly bound excitons, which you can study both type of delocalized and localized excitons in these tungsten diselenide materials, which have higher transport properties. So that was why we chose these materials. So we take a PL spectra just at room temperature of this heterostructure. You basically have optical emission. Like I said, both materials are optically active. So this is the peak that is from the bulk CRPS4 near the more redder region, and this is the peak from the tungsten diselenide exciton at room temperature. And you can see that we measured the copolarized emission from the sigma plus and sigma minus light that is emitted from the heterostructure. We don't really see any change in contrast, and that is kind of aligns with the fact that there is no real magnetic order. It's at room temperature, and the critical temperature is below 37 Kelvin for this for the CRPS4 bulk. So then what we do, we take this heterostructure, we put it in the cryostat, cool it down to about 1.8 Kelvin, so much below its the critical temperature, and then we reevaluate the different spectral range. And here what we see now is the WSE2 intrinsic defect peaks, and this is where the neutral exciton peak is, but it has lowered because now you have the most dominant defect emission at low temperature that you can observe. And these are still defect-based excitons. And this is the different peaks from CRPS4, the intersystem crossing transitions that are present in the CRPS4 material. So you still cannot see a lot of change, but if you really zoom in, you'll be able to see that there is a 7% change in contrast, which is slightly higher than the previous one, which was at room temperature. And that is a signature that there is some antiferromagnetic order present, because of course you are not expecting to see a lot of change, because WSE2 is on the surface of the CRPS4, it is just measuring the surface level magnetization with the presence of different domains that is present on the first layer. So then what we do is we try to use these spatially localized excitons and really see what is happening at the, if you spatially localize, we are like reading out in very smaller domains instead of like averaging over a large lot of domains in the surface layer. And when we do that with the localized excitons, you can see that the contrast changes much more, and we have basically added all of this, and when we integrate that, the mean comes down to 7%. So spatially localizing kind of enhances the contrast because you are getting the advantage of spatial localization. So this is what we get with the spatially localized quantum emitters when we use these excitons to study the interaction with the CRPS4. So all of these experiments were performed without any magnetic field. We are just changing the critical temperature above, below, and we are seeing the change in the contrast by using the degrees of freedom that I defined earlier of the excitons, which were the Valley degrees of freedom based on the polarization contrast so far. So now we apply a magnetic field and we go to the extremes. So we start with minus 8.5 Tesla, and again looking just at the CRPS4 bulk, we see now there is a change in contrast in the CRPS4 bulk, which is basically, you also have the opposite change when you flip the magnetic field, and this kind of gives you the spin flip in the bulk CRPS4 So essentially what this tells is now there is an imbalance in the populations of the moment, because you are of course aligning most of the moments along the direction of the field. So that's that. The bulk CRPS4 is clear. Of course, like if you use the magnetic field, you are magnetizing most of the moments. So now what happens in the other part of the device, which is the WSE2. So when we look through the WSE2, we basically see that there is a flip in the change of the polarization. The polarization changes from the bulk CRPS4 here. So we reverse the magnetic field, we check it in the other direction as well, and you can see here that here it's the same thing. Whatever polarization you had for the bulk CRPS4, it's basically reversed for the surface magnetization that you get as a result of this heterostructure formation in the WSE2 defects. So then next we basically computed the polarization contrast for all the magnetic fields, and this is the trend that we see for the CRPS4. So at the positive field we get this more upward moments, and negative field we get more downward moment, and for the WSE2 you can see that the trend is reversed. So one of the reasons why this is happening is because of the charge transfer effect. So when you put WSE2 in proximity to this CRPS4 material, there is the band alignment, and the band alignment of the WSE2 conduction band and the CRPS4 conduction band gives you a type 2 sort of alignment. And at a specific magnetic field, when you are polarizing all the moments, you are making sure that the charge transfer only happens from a certain valley, and it's blocked from the other valley because of the ways the spins are aligned. So when you do that, normally you are allowing more and more sigma minus light to recombine, and you are basically creating a non-radiative channel because of the charge transfer from the plus k valley to the CRPS4 levels. And this was also confirmed using DFT, where you can take the bulk to even up to a monolayer, and you can see that the alignment always remains type 2, irrespective of the number of layers. And even if you include the spin orbit coupling, the type 2 alignment remains with some change in the energetics, of course. And this again confirms that you are suppressing one of the valleys over the other when you are getting this kind of magnetic order in this material at a magnetic field. So now we zoom into the low magnetic field, and what we see is that the lower magnetic field up until about 1.1 Tesla or so, we see that the material remains in perfectly antiferromagnetic order, and with a slightly decreased value of the rho, and that is again because of the presence of multiple domains in the material, which gives a finite value of rho instead of 0. And this is what we get from the CRPS4 optical emission. So now if you look at the 2D transducer or the optical semiconductor, what happens is you can see at that same zoom in of the lower magnetic field, it gives you a linear effect, which means that it is just simply following the Valley-Zeeman effect as a function of the magnetic field, and the magnetic material basically is not influencing the rho of the 2D tungsten diselenide up to that magnetic field. So this is basically the spin flux transition from where the material changes from antiferromagnetic, and you are aligning all of the spins more and more towards the direction of the magnetic field. And you can see that is the reason why at higher magnetic field, the 2D tungsten diselenide excitons basically saturate in the polarization contrast. And normally, if you just are looking at bare tungsten diselenide, you should not really get any saturation because of the linear Zeeman effect. And this basically further confirms that the 2D transducer shows this linear behavior because of the surface layer sensing of this magnetization. And the non-zero rho in this A-type AFM region shows the formation of these multiple domains when you are transitioning the material from this paramagnetic phase to the A-type antiferromagnetic state. So another experiment to confirm this is to record the Zeeman splitting. So remember how I told you can use both the degrees of freedom, the polarization as well as the splitting. So now we see that the splitting also shows the same kind of behavior, where you have a very linear behavior in this spin flux region between plus minus 1.1-ish or so magnetic field. But then as you increase, you get a saturation of this splitting. And normally if you are looking at bare tungsten diselenide excitons, you can see that the magnitude of the splitting is almost 4 times less at a certain magnetic field if you are keeping track. So, the effective magnetic field at the tungsten diselenide is very, very high, almost a factor of 3 difference than the bare. So, again this is a confirmation that you are actually like measuring the surface level magnetization, because if it was the bulk, then that effective magnetic field would be very, very low, and you are just measuring the top surface of the CRPS4 using this tungsten diselenide. So, this was basically an example where you can do a single shot measurement of both the bulk CRPS4 as well as the surface layer by leveraging on these heterostructure material. So, the other thing that we confirmed is now we switched from antiferromagnetic to ferromagnetic materials to try to repeat and see if we can get the same effect at room temperature with these ferromagnets. And now ferromagnet that we use is FGT, which is sourced from Oak Ridge National Lab, and the heterostructure looks pretty much the same like that. And we are again like see some kind of coupling of the spins in the FGT with the exciton in MOS2. So, for a bilayer MOS2, this is what the PL spectra looks like. So, we get these different excitonic features. So, these are the A, B exciton and the indirect exciton that you see for the MOS2, which is in red, and in the proximity of the FGT there is a shift in the indirect because of the normalization of the indirect points in that way. And then for the direct exciton, you can see you can no longer fit it to a single function, but you have to use like 2 Lorentzians to fit it, which indicates some amount of splitting that is happening even at room temperature. So, you can again like sensing these magnetization of these bulk materials using the 2D TMDC. And this is again the principle behind this is still the same, like you have the 2 valleys and then you have an effective magnetic field, and what you see is an effective a Zeeman effect because of that interaction of this FGT with the 2D tungsten diselenide. So, summarizing the talk, so what we have shown you is single shot detection of bulk as well as surface layer magnetization by using a single magnetic heterostructure in these 2D semiconductors, which are magnetic and optically active semiconductors. And the reason behind this was the spin polarized charge transfer. We leveraged on spin polarized charge transfer to demonstrate that you can use both intrinsic defects and localized defects with different spatial resolution to get to read out this magnetization property. And further, we showed that you can use Zeeman splitting as well as an indicator to confirm that you are in fact reading just the surface level magnetization, and the contribution from bulk is only there in the bulk PL of the CRPS4 and not from the tungsten diselenide sensing layer. So, with that I will end my talk, and this is my group. Most of the work is done by Hassan here, who was leading this project, and then we collaborate a lot. Some of the data EFI helped us to understand a lot of it, and then John Shaw, Anderson, E.G. Shiwang has provided resources, and we source our samples, the magnetic materials from Oak Ridge and the HBN from NIMS Japan, and that some of the TMD work that we are doing right now are with very low density defect of these materials to create the defects on ourselves, and then study the effect of extrinsic defects, which was from Jim Hohn's group, and the molecular foundry for actually like imaging the domains in these materials. So, with that I end my talk, and will be happy to take any questions.